Okay, welcome back. I'm recalibrating here because we just had some interesting back and forth shenanigans. But we're here now on this segment of population growth. And I ended the last section, so we started off with the exponential growth model, which you see now. And I want to reemphasize that there are a lot of assumptions written into this model that you can see the list here, and I won't go over them again, but the bottom line is it really doesn't happen that way, right? It's the null model. And if your population is growing and isn't remaining stable at zero, then that's interesting. That's where it gets fun, and you want to find out why. Okay? If it's a declining species and species that's endangered, you want to know what's going on and what can you do to fix that. If it's a population that's becoming overpopulated and you have the ability to do so, you might want to flatten the curve, as they say. Does that sound familiar? Okay. COVID, flatten the curve. All right, so this is the null model, and your job as an ecologist is to use it so that you can make predictions and then get into some interesting ecology around that, find out what's going on. All right, so that was, the first part was on exponential growth. You could use that for any population. But the calculus, that equation, dNTT equals Rn, may be, not familiar or comfortable for you to work with. Geometric growth, if you can, is a lot more, well, it's algebra, just straight up algebra. And it's good for many species that have births that are pulsed each spring. Humans don't do this. There's babies being born right now behind me at Cross Hospital, I guarantee it. There are babies being born in every continent, except maybe Antarctica, okay? We can't do this. But a quail, as the figure shows here in the lower right, has this pulsed reproductive life history. Every spring, eggs are born, chicks are hatched, and then there's a slow decline of that cohort over time. So they may be present in a later time, but now swamped out by the cohort here from those eyes, 30, let's see, this is the 36 cohort, this is the 37 cohort, presumably. Maybe this is the 36. Yeah, this was the 35. The blue was 35, feeds into the 36. Now it's swamped out by 36 babies. That feeds into 37, but now they're swamped out by the 37 babies, still a few 36 left, etc. Okay? So you see these nice peaks, these are the pulses of spring reproduction in this mountain quail with its cool little tassel. So we have a new term with geometric growth. It's called lambda. It's another Greek letter. It's L. When I write these lectures up, or when I write tests, I'll put in lambda and I have to switch the font to symbol. And then on my computer, it knows to change L to that letter. But then every time I move over to a new system, it changes it all back to English, which I'm always really pleased with because sometimes I don't notice it till it's too late, but I caught it this time. So the new term lambda, Greek L, it's qualitatively similar to R, our intrinsic rate of increase from the exponential growth model. And I'll dig into that more in a bit. It's super easy to calculate, though. It's the ratio of the population size in 1 year to that from the preceding year. And so this figure shows lambda just equals the population nt plus 1 in the future divided by today's population, okay? In a very simple version of this. So there's only 2 years being shown here. Again, the interval could be year, it could be days, depending on the species, or you may be interested in 10-year cycles or something. So those numbers can change, but we'll just, for simplicity, we're calling them years because at least my brain works pretty well that way. So let's look at an example. Let's see. Still without organisms, we're just looking at the numbers. Let's say we want to know the population size of some organism in 2 years, some population. We'll let t sub 0 equal now, okay? And then t plus 1 equals 1 year from now. And we can then say, okay, what about t plus 2, 2 years from now, etc. Can we continue to develop the model out into future years with this simple model of using lambda the way I described in the last slide? And the answer is yes, of course we can. That's where we're headed. So n1 equals lambda. Somehow you've already figured it out from previous year's studies. You've done a pilot study. You know lambda. So you multiply today's population by lambda, and that'll tell you what the population will be next year. Okay? If you want to know what it's going to be in 2 years, you could multiply that. By then, this n1 is this year's population, so it's the same equation, just that subscripts have changed to reflect the following year. But look at this. You can substitute for n subscript 1 this equation. And what would that look like? It would be n2 equals lambda, lambda, n0. So you can use this same equation and say instead of 1 year, you want to look at it in 2 years. You don't have to wait a year to get there. You've already figured out your lambda. So you substitute that lambda n sub 0 in for n1, and you get this n2, 2 years from now, equals lambda times n sub 0 for population in year 2. But you can also see that you could look at those two lambdas and call it lambda squared, right? So now n2 in 2 years equals lambda, which you've already calculated with your pilot study, squared. So this subscript makes it up into here, the exponent. And now you just say, okay, lambda squared times n sub 0 will give you the population in 2 years. And you can imagine what it might look like in 3 years, I hope. What that equation would look like in 3 years. So again, here's n2 equals lambda lambda no, or lambda square, n subscript o, I should say. And you could do this for any number of steps, but it of course gets tedious if you're constantly deriving the equations by plugging numbers in. So just use that exponent, nt equals n sub 0 times lambda raised to whatever time point you're looking at. And so let's see, that would, I guess I didn't give you, I thought I did. No. So if it was in 10 years, it would be n sub t equals n sub 0 times lambda raised to the 10th power, or raised to the 3rd if you only want 3 years, or 100, or 1,000. You get the point. Works for pulsed population growth because the equation to get lambda is very simply this year to the next year. And then you raise it to however many years you're looking at investigating. So predict the population at a future point, and it's only good for a population growing in discrete intervals. This word is a fun word. There's another word that looks very similar and sounds exactly the same called discrete. And discrete reproduction might be reproduction in a hidden space, but discrete reproduction is in intervals. The word actually refers to intervals in pulses. So make sure you spell it right when you say this word in your head. It's D-I-S-C-R-E-T-E, not E-E-T. Okay? Look it up. All right. And then when you add reproduction in there, discrete versus discrete. Okay. A little bit more about the geometric growth model. that helps inform our understanding of how it's applied. We've already defined it, that is lambda, as E t plus 1 divided by t. Okay, that's just for one pulse. Can lambda be 0 or a negative number? No, right? That cannot happen. The reason for that is you can't have 0 in the numerator because you don't have any species. They're extinct, at least locally. So there's no way to get more if you don't have any to start with. That's easy. The other one is sort of mathematical non-starter, but let's say you could start with 0 in the denominator. Well, no, you can't, because you can't have, again, a population start from 0, right? So, no. When lambda equals 1, there is no growth. Okay? We're going to look at how that relates to the rate of increase r in a little bit. But when lambda equals 1, there's no growth. Now, I left blanks here. I'm going to come back and fill them out in a minute. But when the population is shrinking, what do you think lambda is? Is it greater or less than 1? Okay. So if it's shrinking, that says the population today was bigger than it will be in a year. Okay. And you can imagine what would the blank be, and there's a bigger space to help. When the population is growing, that is, next year's population is larger than this year's, lambda would be what? Greater than, equal, or smaller than 1. And hopefully, if you want, you can stop the video and work this through in your head, but I hopefully have given you enough time for those of you that are kind of plowing through it versus those that just go blink. That's the answer. Less than 1, as you probably figured out when I highlighted that you're looking at a population today that is bigger than the population in a year. So just plugging in numbers, population today is 2 and next time it's 1, or 200 and 100. That basically comes out to 1/2, right? So that's less than 1, 50%. And then if you flipped it and there was 2, it's 200 next year versus 100 this year. Now it comes out to 2 instead of 1/2. 2 is, I'm pretty sure still, yeah, it's greater than 1. So you can see very, very simple way to calculate these things and to see the effect of these populations through time. And what lambda tells you. All right. Okay. So for a nice example, we will look at these elephants. Well, not these elephants, but elephants. And it's a made-up example. The numbers I made up, I may have tried to find some numbers that made sense, but I'm not guaranteeing that. I think I just made it up on the fly. So I apologize if these are way off, especially to elephants and to elephant researchers who may be watching. So you work on elephants in Africa. Lucky you. I would like to do that. Large charismatic megafauna. After several years of census work, you estimate lambda to be 1.005. Gee, that's not very much different than 1. The current year population is 500 individuals. How big will the population be in 3 years? Right? So we've already been talking about this. N3 equals n sub 0 times lambda raised to the 3rd power, 3 years. All right? Now we can plug our numbers in. We know n today is 500. We know lambda is 1.005. So we'll plug those into these two variables. There they are. And that equals, and you could do it with your calculator, but of course I already did it for you here. So next year you'll have 5.07.54. Pity the poor half an elephant that comes out. Again, is that the top half or the bottom half, or the right side or the left side, or is it a diagonal slice? Okay, you get the point. On average, somewhere around 507 to 508. That would be 7 to 8 reproduced from 500. Next year, this number you're plugging in might actually be this number if you're starting over. Okay. So, right, elephants. Now let's look at how the exponential and the geometric growth rate are related mathematically. They actually are, as you can imagine. They're both looking at growth. The exponential growth is so named because you're looking at the exponents. I kind of highlighted it, but I forgot to tell you, when we change the exponents, that is the r or the t, rather than the initial population size n, looking at exponential growth, it's the exponents RT that make the population grow super fast, right? Changing n, it doubles every year or something like that. But changing R and T, which are e raised to the RT, that's when populations really soar, really grow fast, or crash because of that exponent factor. The geometric doesn't use the exponent necessarily in the same way. It gets a little bit squishy. But you're looking at lambda year 1 to year 2 to year 3 to year 4. And while there is an exponent, it's the year, it's not nearly as reliant on the exponents because there's only one number that plugs in there versus r and t. Okay, so how do they relate mathematically? There's our geometric growth. Log e times times lambda actually equals the rate of increase from the exponential growth. Log e times lambda from the geometric equals r in the exponential model. Okay, that's pretty important. And you can rearrange the equation above to come up with this equality. Lambda actually equals e to the r. Right? So they are directly related. The geometric growth is an exponential growth. I don't want to get hung up on this too far because it'll get confusing, but I just want you to see that they are very much related to each other. But we call the exponential growth model that one that uses e to the RT, and we call the geometric growth model the one that uses lambda. Okay? And so you could actually have the same, very similar equations with the different models. And when you model them, the figure that comes out, that is that curved line that starts slow and gets fastly, goes quickly high in terms of population growth. It's going to look exactly the same. And indeed it does. So look at here, we have 3 different figures. On the left side, we have a declining population size on the y-axis over time. And here we have a population that's declining. And then in the middle, we have a stable population. There's no growth, no declining. And then on the right side, it's a population that's growing. And you can see the other feature here. It doesn't matter which model you're using. These same curves are the result of your manipulations of the data with those models. In this model with declining population, lambda would be less than 1, and I showed that in a slide a ways back. The rate of increase, intrinsic rate of increase, would be less than 0. Note that the intrinsic rate of increase is 0 when there's a stable population. There is no growth, there's no decline, and it's a flat line. Rate of increase is 0. It's not positive, it's not negative. Lambda is 1. You're just multiplying 1 back on itself, and it's just 1. So if it's 1,000 individuals, multiply it by 1, it's going to be 1,000 individuals next time, right? And then a growing population, obviously, is different. So R is greater than 0. You're constantly increasing. And lambda is greater than 1. Okay? The one thing to keep in mind, and let me see something real quick. No, I did not. Yeah. Took out a slide that I wish I had left in, but I'll just use words here to describe this. So the continuous growth model, that is the one that uses R and infinitesimally small intervals, we'll just use the growing population side here on the right, gives you a very smooth curve, okay? But when you're doing the geometric growth model that is using pulsed reproduction, if we had, using my laser, let's say year 1, year 2, year 3, year 4, you're going to see the numbers or the dots clearly. Let's see if I can make this happen. I should have put in that other figure. Where am I? Yes. Yes. Okay, a pen. This will be cool if I can do it. Okay, so let's say year 1 is here. It's a nice little dot, isn't it? Year 2 is here. All right. Year 3 is here. Okay, bear with me. Some of you are saying, yeah, okay, thanks for that. This is where I'll define ecology in a minute. One of my favorite definitions from my master's, given to me by a plant taxonomist, when I complained to him that I thought plant taxonomy uses a lot of sort of hand waving to understand which group belongs to which species and subspecies and variants, and that hand waving that Darwin talked about. Anyway, I'll come back to that. So this is the geometric growth model, and in fact, look what happens. You don't get a smooth curve. You can actually draw a smooth curve, but the data points could be connected with only straight lines. If I had the ability to make a straight line with my fingers on this computer, this is what it would look like. And so the pulsed reproduction, I just can't get a straight line. Kind of there? All right, whatever. You get my point. The pulsed reproduction is not a smooth curve. Infinitesimally small continuous growth of the exponential growth model, or continuous growth, where babies are being born constantly, then you get a nice smooth curve. You can model the other one to be smooth, but actually it's just drawing lines between your dots, and your dots are well spaced, so it's probably not, you're interpolating, but there's no reproduction in between these lines, right? It's year 1 to year 2 to year 3. There's no reproduction in between, but you can draw a line to make it seem like it. Okay, I'm belaboring a point there. They are related. These continuous growth models give you curved lines that are beautifully smooth. The geometric do not, but we often use the same kind of figure even though it's not realistic. Okay? Right. Populations go up, populations go down. But even when they're going up, there has to be limits on growth, or we're going to be, well, there's an example, I think it might have been in Origin of the Species by Darwin, looking at elephants, or someone did it later, I think, where if you started with 2 elephants and they had a certain growth rate, which was not unrealistic, within like 100 years, we'd have elephants. I'll bring in this in the next lecture, but something crazy like as tall, we'd be as deep in elephants in New York as the Empire State Building. Something like that. I have to go back and find those data. But if there's unlimited growth, species will cover the planet quite deeply, and we're going to be in big trouble. There is limits out in nature, but also, through other things like, well, I guess you can call humans part of nature, but we limit growth ourselves, and we can manage our populations that way. That's sort of a different topic. But just intrinsically, if you will, populations do not grow until they reach that huge number. When they do, watch out, which is a big reason why we're worried about the human population growth. It seems unchecked. And maybe this year it is getting checked with COVID, but it's not sustainable, to throw a good word out there to talk about this. So in the next section, I'm going to get into sort of natural checks on population growth and why we're not knee-deep in salamanders or whatever your organism of choice is. Okay, so good. That's it for today's segment, and we'll catch you next time when we get into checks on population growth. Thanks.